Okay, let's continue. I, I forgot the last slide from lecture 7. So let me uh, continue with this lecture. Okay, so great. So what was the conclusion from the lemma? Well, I guess let me get back to the slide. So we have a mixed integer linear program, and the idea was to take the convex hull of possibly a discrete set. And so we got a convex problem. And in fact, the convex hull by Mayer's theorem, the convex hull is another polyhedron defined by a finite system of linear inequalities. So you can just solve. So what it means is this mixed integer linear program is equivalent to another linear program without an integer constraints. Okay. So then, does that? Well, we know that integer program is NP hard to solve, but linear programming is polynomially solvable. What I'm saying is, well, okay, again, an integer program is equivalent to a linear program, but somehow there's a complexity gap. Uh, is there a contradiction here? Well, the answer is no, because there's still a part to convert an integer program to a linear program. So the Mayer's theorem is not constructive. It's not algorithmic. It only talks about the existence of an equivalent system, A prime, G prime, B prime. It doesn't give you this. It doesn't compute this equivalent system to you. In fact, finding such a system takes an exponential time. And in fact, the number of inequalities to write down can be exponentially many. Okay, even writing down this system can be exponential. So the answer is no. Still, there's a complexity gap. Okay. So, like one of the main directions in integer programming is to come up with a system like this. Okay. How do you find it? Like we have an integer program with linear constraints, and can you derive an equivalent linear system? And somehow maybe even if like there are so many linear inequalities in the equivalent system, can you still solve a linear program in a polynomial time? That is main question. That's what we are gonna discuss in lecture 5, like lecture 8. Okay. Any question before we start? Okay. So that's so this is the last part of the matching problem. So we're gonna end with the matching polytope. Okay, and I'll discuss a bit about separation. I guess many of you who have experience in integer programming, you guys perhaps know already about the separation problem. You have some constraints and you generate cuts and you define your branch and cut procedure. Okay, this is a typical way of solving your problem. But I'm gonna lay down the theoretical foundations for that. Okay, the branch and cut framework is already quite common, but maybe some of you are not aware of the theoretical foundation behind it. I'm gonna present the right result before that. Okay, so the matching polytope, and I'm gonna talk about the ellipsoid algorithm that shows that if you can solve the separation problem in polynomial time, then you can solve the corresponding optimization problem in polynomial time. And that complexity connection is done by the ellipsoid algorithm. And this is due to, I guess, Grochel, Lobas, and Scriber, and they got the Fulkerson Award by this result. And I'm gonna explain that. And the matching problem can be solved using the separation. I'm not going to talk about the separation algorithm, but I'll explain how we do it. Okay. Anyways, so So remember that, so this, we have this in binary linear programming formulation for maximum weight matching. So we just write down the degree constraints and impose that the variables are bounded, are binary. Okay. When your graph is bipartite, then we relax the binary constraint and we have the non-negativity. Okay. But let's look at this odd cycle, cycle of length 3. Now, let me compare the solution for the integer program and the solution to this LP relaxation. Okay. And if you solve the integer program, we know that it gives you a maximum matching. And this is one solution. So I have 1, 0, 0 for the other edges. And this is for the case where the weights are all 1. Okay. But if you solve the linear program, if you look at the LP relaxation, what I have is I have 3 constraints for the 3 edges. So x uv plus x vw is at most 1, and x vw plus x wu is at most 1, and x uv plus x wu is at most 1. So I have these 3 constraints for the 3 vertices. Okay. But you know, in the LP relaxation, you don't have to take 0, 1 values. So I'll take 1/2 for all variables, and you realize that you know this solution satisfies this linear system. Okay. But now the objective value is when the weights are or 1, the objective value is 1/2 plus 1/2 plus 1/2, which is 3/2, which is greater than 1. Okay. So when you have an odd cycle, the maximum value of the LP relaxation can be strictly greater than the maximum size of a matching. Okay. So you cannot use this LP relaxation when your graph is not bipartite. So that is the idea. So so we need to define this notion of the matching polytope. Okay. So the matching polytope is the following. So in the previous lecture, what we saw was that you know when you have a discrete set of solutions to an integer program, it's equivalent to optimizing over the convex hull of the solutions. So the matching polytope is basically the convex hull of the solutions to the matching problem. Okay. Again, we proved that you know taking the convex hull gives you the same optimization problem. Well, it gives you the same objective value. So the question is, what is the convex hull? How do you, and that is called the matching polytope, which is the convex hull of the solutions to the integer program, to the integer programming formulation for the matching problem. Okay. And again, we saw that, you know, this is equivalent to the original integer program. Okay. So this is the matching polytope. And how do you find the matching polytope? Well, what we can prove is that for a bipartite graph, you just replace the binary constraints by x at least 0 and at most 1. So this is 0, x at 1. Then this gives you the matching polytope for the bipartite graph. Okay. Well, I mean, this follows from our previous discussion, but let's prove this together. Okay, let's denote this by some polytope P. By the way, this is a polyhedron, but this is bounded because all the vectors are contained in this 0, 1 box. So this is a polytope. So suppose that P is not equal to the matching polytope. But we know that the matching polytope has to be contained in P because all matching, the incident vector of a matching, satisfies these linear inequalities. So the matching polytope itself is a subset of the right-hand side. Okay. So it means that then there exists X bar that belongs to P, but not the matching polytope. Okay. Then there's the nice tool called by the separating separating hyperplane theorem. So what it means is when you have a closed convex set and a single point that is outside this closed convex set, there's a hyperplane that separates these two. There exist. Well, the separating hyperplane theorem does not just works for this singleton. It can work for general closed convex sets. But let me just stick to this version. If you are interested in the original version, you can search the web, and you will find many versions of it. There exists W R E such that W transpose X bar is strictly greater than W transpose X for all X. So that means that if you take the maximum value of this thing over the matching polytope, you have this relation. Okay. But well, we proved that max W transpose X such that X belongs to, so this is P. So this is at least W transpose X bar, just because X bar belongs to this set P. And we proved that this is greater than max W transpose X, and X is belongs to the matching polytope. This is what we argued. But this one, so what is this, the leftmost side? This is, well, we optimize this linear function over the system with this inequality. This is the value of the LP relaxation. Okay? And the value of the LP relaxation is equal to what we proved from, I guess, from slide lecture 3 or 4, that solving on LP gives you a maximum weight matching. So this is the max weight of a matching with weights given by this W. This is what we proved. It's enough to solve a linear LP relaxation, and that computes the maximum weight of a matching. Well, this one itself is also equal to the maximum weight of a matching. Okay. Well, because we proved that this thing is equivalent to solving the integer program. But we have the strict inequality, so this is a contradiction. Okay. So this is one way of proving that the convex hull is written by some system of linear inequalities. Okay? This is one way of solving it. Great. So, uh, so for bipartite graphs, we just write down the degree constraints and the bounds between the 0, 1 bounds on the variables. That gives you the matching polytope. But you know, for an example of this 3 cycle, we know that 1 over 2, 1 over 2, 1 over 2 belongs to the polytope P, which only has its bound constraints and the degree constraints. We saw that x uv plus x vw m was 1, x vw plus x wu m was 1, x uv plus x wu m was 1. So 1 over 2, 1 over 2, 1 over 2 satisfies all these constraints. So it belongs to the polytope P. Okay? But this thing doesn't belong to the matching polytope. Okay, just because the 1 over 2, 1 over 2, 1 over 2 that has the the greater value than the maximum rate of matching. So what it means is that for a non-bipartite graph, the degree constraints are not enough to uh, describe the convex hull or the matching polytope. So we need to write down some inequalities to discard, to forbid this point from my matching polytope. And the idea is the following. I'm going to take an odd number of vertices U with at least 3 vertices. Okay. So if you look at this example, I took a subset of 7 vertices. Okay. And what I'm going to do is I'm going to count the number of matching edges that are fully contained in this set. Being fully contained means that 2 endpoints of that edge are part of this set U. Okay. But because I took an odd number of vertices, okay, one edge, one vertex has to be left out if you just look at the points inside this odd set. That was the case for the blossom. So the blossom is an odd cycle, and there's vertex U that is not covered by a matching edge inside. Okay. This is another example. So basically, what it means is if you count the number of matching edges that are fully contained in this set, has to be at most you divide U by 2, and because U is odd, it's less than or equal to U minus 1 divided by 2. That's because you subtracted 1 from U because at least one vertex is unmatched within the edges of inside the set. So, and each edge can cover 2 vertices, so we divide it by 2. So this is the equalities. Any question? Okay. Let's prove formally why this is valid. Why the solutions to the integer program satisfy this inequality. Let us formally prove this. Uh, uh, Yeah, so we know that for each vertex u, let's write down the degree constraint x, u, v, and most 1. Okay, so this holds for all u. This was the degree constraint. And I'm going to add the degree constraints for all vertices in this subset U. Okay. Then the right-hand side will become the size of the vertices, the number of vertices in U. Okay. Then let's look at the left-hand side. Uh, uh, I don't know. I'm going in the right direction. Uh, so let's look at the set U. And there are edges that are contained in U. But some vertex might have an edge that crosses this subset. It could have a neighbor that is outside this vertex U. Okay. But let's look at this edge. That this edge is counted twice. It appears as on edge of this vertex, and also it appears as an edge of the other endpoint of this edge. But this edge that crosses this subset appears only once. So this is equal to 2 times the summation of edges that are fully contained in this subset plus the edges that are crossing the subset, which is denoted as delta of U. Those edges appear only once. Okay. So the left-hand side can be written as this. So we have the inequality that this is at most U. We know that these variables are at least 0, right? So this implies that 2 times E for the edges that are fully contained at most U. Okay? Now we divide both sides by 2. We get U over 2. Okay? We got this inequality. And the last step is the following. We know that these are integers. Each variable is 0 or 1. So if you sum up these variables, that's an integer. But if you look at this quantity on the right-hand side, this has a fractional part of 0.5 because the U has an odd number of vertices in there. Okay? But the integer value is less than or equal to something like 2.5. But it can take an integer quantity. It means that it is less than or equal to 2. So you can actually subtract 1 from the right-hand side. You still get an inequality. So this is why the inequality is true or valid for all solutions to the integer problem. Okay. Any question? Okay. Great. So, and in fact, so for an example, we get back to this example of 3 triangle. we write down, so we take all three vertices for this odd set. Then the corresponding odd set inequality is xuv plus xvw, xwu, because all three edges are fully contained in this set. So at most, u has size 3, and you divide it by, you subtract 1 from it and divide it by 2, that has value 1. So this inequality is the corresponding odd set inequality, right? But now we were worried about the solution that takes 1/2 in every component. The summation is at most 1, or the summation is at most is 3/2, but it has to be at most 1. So if you impose that odd set inequality, it's going to ignore this solution or forbid this solution from your set. So in fact, the matching polytope for a general graph is obtained by adding all possible odd set inequality to the degree constraints. Okay, so this is the matching polytope for general graphs. The proof is not too complicated, but can be quite technical for this lecture, so I'm not giving you a proof. But if you are interested, I guess there are many materials available for the proof. So this is one of the classical results in combinatorial optimization. Okay. Yeah. Uh, that's a good question. Uh, uh, but I suspect that there's an example uh, showing that that's not enough. But that's a good question. But I think you need to enumerate all possible odd sets, which doesn't have to be uh, an odd cycle. But that's a good question. Yeah, you can think about it. Just try finding an example. I guess then you get something. Any other question? Okay, then let's move on. So then, okay, so let's look at this theorem. Now, we got a complete characterization of the matching polytope. So we got only linear inequalities. We don't have any binary constraints on variables. So that means that we can just optimize a linear function over this. Okay. But one issue is that, well, okay, the number of degree constraints is equal to the number of vertices, but the number of odd set inequalities is equal to the number of odd sets. And you have to enumerate exponentially many combination of odd number of vertices. Okay. So writing down the entire set of inequalities is expensive. That's not what you want. So I guess again, for those of you who are familiar with the branch and cut framework, you just keep you know, the degree constraints, and you add this offset inequality only if there's a one where the corresponding inequality is violated. You add it and you solve the LP relaxation. And if there's a cycle, there's an offset for which the inequality is violated, then you take it and you add it to the system and you repeatedly solve it until you get on a solution that corresponds to a matching. Okay, that is the branch and cut framework. Um, uh, but that works nicely for in practice. But now I'm gonna I'll give you a theoretical justification behind it. Okay. So that's given by the ellipsoid algorithm. I'll give you some outline of it. So the ellipsoid algorithm does the following. So you are given a polyhedron. Okay, I'm looking at the feasibility problem over this polyhedron. What it is you want to, so given this polyhedron with this system of linear inequalities, I want to decide whether the interior is empty or I want to find a solution that's inside the interior of it. Okay. If the problem, if the what it means is if the corresponding LP is feasible, I want to exhibit find a feasible solution, or I want to prove that there's no feasible solution. And this is called the feasibility problem. Okay. For some problems, like finding a feasible solution is too easy. Like for the matching, you can just take the zero vector. That's always feasible. But in fact, for the complexity perspective, feasibility problem and optimization problem are equivalent, and it's for linear programming. And that's, I guess, let me explain first here. So what it is you can do a binary search. So let's say I have a linear uh, objective of minimizing C transpose X over AX at most B. So this is the typical linear program with an objective. And solving an optimal solution is equivalent to uh, um, solving a log number of feasibility problem. So that is there a solution? Is a point in this polyhedron which keeps the original set of inequalities, and among them, can you also achieve a value lower than V? Okay. If there's and then you run your ellipsoid algorithm to detect whether there's a solution contained in here, then good. Then that is a feasible solution to this linear program whose value is at most V. And what I do is I lower this level V, okay? And then I run the ellipsoid algorithm one more time and, then tries to find a feasible solution. And you repeat until, you don't have a solution. That will be then that corresponding, the last value V will give you the optimal value of this linear program. So the feasibility problem is equivalent to the optimization problem. Okay. So then let's get back to the original feasibility problem and how do we solve this? Yeah, and the answer is the ellipsoid algorithm. And well, I guess I don't like having all these sentences at the same time, but well, let's explain it. Okay, so we have this ellipsoid, and the ellipsoid is nicely designed that I know the characterization of its center point. Okay. Okay. If this center point is not feasible, if the center point satisfies, let's say this is xt, if satisfies the linear system of inequalities, then I'm good. This is a feasible solution. Okay. But if not, then somehow the polyhedron is located somewhere. I mean, the polyhedron is P. P is located somewhere. And I know that my center point is outside. I mean, this center point is outside the polyhedron. Then what you do is you find the separating hyperplane. So you draw a separating hyperplane, and you find another ellipsoid that is under this separating hyperplane. Let's say you take this thing. and you compute its center point, and this is xt plus 1. If this belongs to the polyhedron, then you're good. If not, you again draw a separating hyperplane and draw another ellipsoid. You repeat this procedure. So this is the ellipsoid algorithm. This is a basic outline, but I guess which ellipsoid you have to choose? That's an important question. And so in fact, Katian proved that this algorithm, you can design a sequence of ellipsoids and which gives you a polynomial time termination of this procedure and solves the feasibility problem. Well, in fact, Katian was not the one who proposed the ellipsoid algorithm. He's the one who proved polynomial time convergence. Okay, and now like this theorem, the ellipsoid algorithm is always, I guess, credited to him, but he was not the one who proposed this idea. Okay, great. Great. Any question? So this gives you a polynomial time algorithm for linear programming. Okay, so the ellipsoid has a nice structure. Again, you can fix the okay. So it has a special structure, and it can be well, in fact, you don't have to use a structure like the ellipsoid. You can take any convex set and containing like, and you can separate at least you can characterize a point inside that convex body, then you are good. But the ellipsoid is good that computing on kind of nice ellipsoid satisfying certain property, such as it has to belong to this half space. That can be done in kind of easy way. That's why. Well, but the way I explain the algorithm is not specific to ellipsoids, but I guess implementing this, you need this idea of ellipsoids. Okay. Yeah. Right. You have to take a large ellipsoid. Yeah. This picture is misleading. Yes. Yeah, you're right. Yeah. So I guess if you stop when if there's if the algorithm found a feasible solution, you would have stopped before you conclude. I think that is. In fact, I've written down this algorithm like many years ago. Maybe I was wrong. Let's see. You would have stopped if you found a solution. So if you kind of got out of this for loop, yeah, you have to go beyond, go below and for here. I think you're right. Yeah. Sorry about this. Thanks. Thanks for correcting this. Any other question? Yeah. How do I set the t? Okay, this is the tricky part. I'm not explaining this in this slide, but I think that's the main contribution of Katian, I think. Yeah. So you have to stop when your ellipsoid gets sufficiently small and something like this. I don't remember the exact details of how it works, but I guess you have to be also worried about when your polyhedron is bounded or unbounded. Bounded case is easier, but I guess when your polyhedron is unbounded, um, if it's unbounded, it's or unbounded in a sense that when there's an infinite ray, you could still have like I mean, you can easily decide whether AX equals 0 has an unbounded direction. That's easier than finding a feasible solution to this AX equals B system. I guess like I shouldn't say more than this. I'm not remembering the exact details. Any other questions? So this is on the ellipsoid algorithm. I guess this is not so useful to you. Like I'm not. Well, the reason I mentioned this algorithm is that it can be used somehow for our next purpose. Okay, but I'll not. Unfortunately, I will not explain how the connection precisely. But I'm just mentioning that this algorithm is somehow applied in combinatory optimization problems, and that's the next result. So I'm gonna state this fact that, you know, optimization and separation are equivalent. And so what it means is I'm going to define this notion of the separation problem and also the optimization problem. So let's say that I can solve the separation problem in polynomial time. Then you can convert the algorithm to an algorithm for the optimization problem that's based on the ellipsoid algorithm. Okay, I'm not explaining the exact details of it, but that is the statement. Conversely, if you have an algorithm for solving the optimization problem, then you can convert it into an algorithm for the separation problem using the ellipsoid method. Okay, that is the equivalence between optimization and separation. Okay, so here's a theorem. So you have the separation problem. So what is the problem? So I have a polyhedron P, and so think of it as a matching polytope. Okay, so we have a matching polytope, and I have a solution X bar from solving some LP relaxation of the matching problem. And I want to determine whether this satisfies all constraints defining the polyhedron. That is the separation problem. If it satisfies all constraints, meaning that it belongs to the polyhedron P, then I want to prove that. If it does not belong to the polyhedron, then I want to find the proof that it is not part of the polyhedron, and the proof will be encoded as an inequality separating hyperplane. Okay, so that is a separation problem. In picture, I have a polyhedron P. If X bar belongs to P, then I want to prove it. And if it's outside the polyhedron P, then I want to exhibit a separating hyperplane. That proves that this point is not part of this polyhedron. So this is the separation problem. Okay. And the optimization problem is, well, you are given this polyhedron P, and I want to, let's say, maximize a linear function C transpose X over the points in P. So this is the optimization problem. So these are two separate problems. But what Grotzel, Lobas, and Scriber proved using the ellipsoid algorithm that, well, the separation problem can be solved in polynomial time if and only if the optimization problem can be solved in polynomial time. Okay. So we use the idea of this separation, separating some inequalities for your system, for your problem, let's say offset inequality for the matching problem, within a branch and cut framework. But this lays down the theoretical justification for the method. In terms of complexity perspective, there's a polynomial time overhead between separation and optimization. Okay, that's what it means. Any question? All right, so let's look at the matching problem. So again, we have the degree constraints, and we have this exponentially many odd set inequalities, right? And this is the optimization problem. Okay, and by the previous theorem, to prove that solving this linear program can be done in polynomial time, what we need to show is that separation problem over these inequalities can be solved in polynomial time. That's what we need to do. So, but let's say x bar, we have this x bar. So proving or finding inequalities that are violated by this point x bar from the degree constraints and the non-negativity is easy, because you go with there are v number of degree constraints and there's this e number of non-negativity constraints. You can just enumerate one by one, and we can check whether they are satisfied by this point x bar. But the question is, what about this offset inequalities? Enumerating one by one takes exponential time because there are exponentially many such inequalities. So we need to have a different method. But the equivalence between separation and optimization says that if you can separate, or if you can prove that x bar satisfies all these inequalities in polynomial time, that will be not enumerating all. So that has to be, different from enumerating all inequalities. But there somehow you can prove in polynomial time that all inequalities are satisfied. Then that means that solving this linear program can be done in polynomial time, and that's done by something called the minimum odd cut problem. You might have heard of like max flow min cut theorem. You find the subset of or minimum size of an edges that gives you a cut. But we are taking on odd cardinality set, and this is related to the minimum odd cut problem. And to solve this, something called the Gomory-Huth tree is involved. And I figured that might be out of scope for this lecture, so I left it here. I heard that some, I guess, students from Professor 권창현 교수님, some of you are maybe working on the B matching problem for weak routing, and he was mentioning some problem of separating some class of inequalities, and I think that might be related to this one. If you guys are interested. Okay. Any question? Yeah. So it doesn't have to be part of the set of constraints defining the problem. But typically, like when you prove that the separation problem can be solved in polynomial time, it's typically that you find one of these things. Because that's more practical, because you know that these inequalities define your problem. So if you can find out some of them that are being violated, you can just add it to the system and you resolve it. So this is more relevant in practice. Okay. Any question? So I'll get back to this approach of separation in the afternoon for a completely different problem, which is submodular function minimization. So submodular, just to kind of give you an advertisement, I guess in the afternoon, we're going to deal with some nonlinear function class. So we were all talking about linear functions, like the weight of a matching can be expressed in terms as a linear function of your decision variables. But in many problems in practice, the objective function, such as like utility or some objective, are nonlinear in your decision variables. And submodular functions provide a nice framework for modeling nonlinear relationships between variables. And we're going to discuss minimizing submodular functions and maximizing submodular functions. But when you minimize the submodular function, you can we'll provide like separation based like branch and cut method for solving that, and that guarantees a polynomial time solvability. Okay, that will be the story for the afternoon, and tomorrow again, I guess lecture 11 will be about something called black box optimization, which is I think quite relevant in practice, because if you look at practical problems, often the problem parameters are not given to you, so you need to make decisions with some limited information about the problem setting. You need to learn the problem parameters, or you have to make decisions based on some kind of global search. So lecture 11 will be about that. And lecture 12 is about my own research projects, and that's about some theory of reinforcement learning and sequential decision making. Okay. So this is it, and I'll see you in the afternoon.